Okay, so this is lesson number 9. It's our third last lesson for this unit, and it's on models of the atom. I'm only going to do 2 lessons this week because I got 2 activities for you. One is on an online simulation, and the other is an activity that you'll do at home with someone else. Maybe get your parents involved. They'll be real excited about it. So today is models of the atom. And I know we've done models of the atom since grade 9 or even before. There's a lot of overlap with chemistry in this lesson. So I'm going to try and really look at it from more of a physics point of view that you might not have seen it from this perspective before. So first, on your screen here, what do we have? We have a radio transmitting tower, and over here we have a house with an antenna. Now this little white ball is just an electron. White ball. Blue ball. This little blue ball is just an electron. Now if it's just sitting there, nothing happens. But if we oscillate it, and oscillating pretty much means I'm causing it to accelerate. And a charged particle that accelerates emits electromagnetic waves. Okay, and here you can see the electromagnetic wave being emits. And due to resonance, we can have this electron match that wave and it gets received by your antenna. So the main thing I want you to take from this is that charged particles, when accelerated, emit electromagnetic waves. So moving from that, let's go and look at the planetary model of the atom. So this is where we're going to start. We're not going to start with J.J. Thomson's model. We're going to start with the planetary model. This is the one most people are familiar with and actually believe to be true. Right? It's just an electron orbits the nucleus, just like a planet orbits the sun. It's very easy to picture. But here's the problem. Moving in circular motion means you're accelerating. If you're accelerating, you're emitting electromagnetic waves. If you're emitting electromagnetic waves, your energy is decreasing. And so that electron should spiral in towards the nucleus. And technically, no atom should exist. Now, we know that's wrong because, well, we exist. Right? But you can't have the electron just stand in one place, not accelerate, because then the electromagnetic force between your positive nucleus and your electron would just attract it together, and same problem. So what's happening then? How can you get an electron to move around a positive nucleus without accelerating? Well, why don't we stretch it out like a ring? And if you haven't tried this, definitely try it. If you have any like ring-shaped object that floats, right, put it in a little bit of water and spin it. It emits no waves. Now, if you put your finger in the water and you go like this, you'll be emitting water waves, right? But if you put like a donut, don't put a donut, what a waste. But if you did put a donut in there and spin it, it wouldn't emit any waves. So this was the idea. Right? Why don't we stretch that electron out into a rotating ring? And then you can actually spin it. So it won't collapse into the center because it's moving, but it also looks static. So it's not going to emit any electromagnetic waves. There is a few problems with this though. One, if you actually go to observe an electron, you observe it as being a point particle. It exists in one location, not as a ring. Right? And also, if it was a ring, right, the electromagnetic forces would cause it to just break apart due to the repulsion with, well, itself. So, good idea, but doesn't get us all the way there. All right, standing waves. You remember doing this in grade 11? You shake the slinky, and you would get this standing wave. The wave would go one direction, would reflect and come back, and the exact wave would interfere with itself, creating areas of nodes and antinodes, right? Areas of constructive and destructive interference. So what if an electron did that? An electron acting like a wave moves around an atom, interferes with itself as it moves in the opposite direction around the atom, and causes areas of constructive interference and destructive interferences, or nodes or antinodes. Well, this makes perfect sense. Right? This means it's sort of looking like a wave, but it's also a particle, right? Another big, what's the word I'm looking for? Another big takeout. Can't think of the word. Another big takeout from the wave-particle duality is the structure of atoms themselves. Now you have to remember that this wave is not a wave of position. Remember, we went over this. It's a wave of probability. So these areas of constructive interference isn't where it is, it's where it could be. Okay? And these areas of constructive interference, these nodes and antinodes, are what give you all these wonderful shapes. Right? Where you learn in chemistry your SPDF orbitals, but those flower-like shapes are due to wave interference and creating areas of nodes and antinodes, which are areas of probabilities where you're more likely to find the existence of an electron if you observed it and collapsed the wave function. And that we call a quantum model, which sort of looks like a cloud. You probably see it in chemistry class where you just do like a cloud. Right? We like to think of clouds in physics because a cloud is something that exists in multiple different states that you can't really observe. And if you did, well, it wouldn't be a cloud anymore. All right, how lasers work. Now I'm going to actually not go through this because there's a great video that's going to go through it from Minute Physics that I'll post. So make sure you go take a look at that. But you can go over my PowerPoint if you want to. That's always online for you. All right, going back to chemistry. Physics, actually. But the atomic emission spectra. You've seen this in chemistry. When you have a gas excited, right, you get those electrons being excited to a higher energy state, and then they drop down. They emit light, which is directly related. The wavelength of that light is directly related to the amount of energy that was given off as it drops down to another energy level. And now we have different series. The Balmer series, for example, is a great equation that you can use here with R. That's the Rydberg constant. And you can determine the wavelength of the light that's given off as it drops from any of these n energy states down to the second one. If you drop down to the first one, that's the Lyman series. If you drop down to the third one, that's the Paschen series, and so on and so on. Okay. If you want to know the exact energy at a specific level, well, this is the equation. It works for hydrogen, only hydrogen. Okay, if you want to know like very, very specific energy levels, then it's much more complicated math. So we're just sticking with hydrogen, right? Notice that it's negative, just like gravity. You're stuck in that energy well. Okay, and this equation also tells you the energy in electron volts, not joules. So pay attention to that as well. Okay, so with that, you can try the questions on the back. Question 1 says, let me make this bigger. Question 1 says, calculate the energy level of the n equals 6 state for hydrogen and state it with respect to the ground state. Okay, so you're doing the En, but we're doing n equals 6. So that's minus 13.6 over, well, n squared. And that gives us electron volts. That's not too bad. We can just sub that into our calculator. We have minus 0.38 electron volts. Pretty simple, plug and play. The next one's the same. It says determine the wavelength of light emitted when a hydrogen atom makes a transition from n equals 5 orbit to n equals 2 orbit. Again, we're only doing hydrogen, nothing else. Okay, anything else gets way more complicated. So stick with this simple equation. Here we have the 1 over lambda plus the Rydberg constant times 1 over 2 squared minus 1 over n squared. right? Sub in your Rydberg constant, 1.097 times 10 to the 7 per meter. I'll just leave the units out. Over 1 over 2 squared minus 1 over, is it 5? 5, yeah. 5 squared. Okay, now when you solve for that, you're going to get a big number, 2303700. Some students leave it there and write meters. A light's not going to have a wavelength that big. So just remember this is 1 over lambda. So take the inverse, and you should get it to be 434 nanometers if you convert it to nanometers. But I'll post these on with the lesson. Okay, so the math isn't too bad. All right, now moving on. If you want to go through this PowerPoint, you can. It's a little bit more advanced stuff that you don't really need to know at this level. But I go over quantum dots eventually, or you might already see TVs that say quantum dot on it. Okay, it's an advancing technology right now, and it uses semiconductors. But what I'd like to talk about with semiconductors is how LEDs work. We usually do a lab in class where we measure Planck's constant with LEDs. Since we can't do that, well, at least I can do is tell you how they work. So let's take a semiconductor. What's a semiconductor? Well, it's a poor conductor, right? And those are the elements on your staircase. So for example, on the periodic table. So for example, silicon is a great semiconductor. Okay, so here's silicon. Now, if you remember, silicon has 4 outer electrons. Kind of getting back into chemistry. So if I were to create sort of a silicon lattice here, or crystal structure, you'd have silicon, and you would have 4 electrons, and they each share with another one. It's really nice crystal structure. All right, so what's an N-type semiconductor then? Well, what we're going to do is remove one of those silicons and put in an impurity, like phosphorus. Phosphorus has how many outer electrons? 5. So it's got this one extra one just floating around, some free electron there. Okay, so that's an N-type semiconductor. Your other type is a P-type, where what we're going to do is we're going to introduce a different impurity, say boron. How many electrons does it have on the outer orbit? Well, 3. So that means we have this hole where there's an electron could fall into. Then what we do is we take those two semiconductors, the N-type and the P-type, and we put them next to each other. Okay, and this is what a diode is called. All right, so what's going to happen here is, well, what do you think would happen? Hold on, my animation's not working. There we go. Some of those electrons might want to go over and fall in those holes, and that's exactly what does happen. But then this creates an electric field. And that electric field prevents any more of those electrons from being able to cross. Okay, so what do we do then? Well, we need to give those electrons enough energy to cross over the field. So we apply a power source, some sort of potential difference, to give these electrons enough energy to cross the field and fall into that electron hole. As their energy level drops, they emit a photon of light. And they go, some will go back through the battery. It creates a circuit, right? They pass the electric field, fall into the hole, right? And then emit light proportional to the energy that is lost. Okay, so that's how an LED works. Now we say an LED is a diode, it's a light emitting diode. A diode means electricity can only flow in one direction. So what that means is if you were to accidentally hook up your circuit or your battery the wrong way, all that happens in this case is it causes that electric field to be even stronger and does not allow anything to pass. Right? So whenever you're using LEDs, if you hook it up the wrong way, it's not going to turn on. And the rest is the lab, which we're not going to get into. Okay, so that's it for that lesson. I'm going to post a couple other videos, which I think are great to watch. And I'm also going to post one video that's a bit long that's going to go into the history of the quantum model, much more deeper than I went into. And it's a good review also of a lot of the things we've been talking about up until now. Right? It's a little bit a strange video, but definitely a good review. So look through that video as well.